At the Jet Propulsion Laboratory in Pasadena, inside Building 264, where the Solar System Dynamics Group studies the motion of objects across the sky, a routine update quietly turned into something far more significant. It was February 27, 2026, exactly 3:18 p.m. Pacific Time. A trajectory analyst sat at her workstation performing a task she had done many times before. Since July, she had been updating the predictive orbital model for an unusual object moving through the solar system. The procedure was familiar. New observations arrive from telescopes around the world, the numbers are entered into the model, and the predicted path of the object becomes slightly more accurate. Most of the time, the adjustment is small. The model refines, the trajectory settles, and the numbers move closer to the original estimate. That afternoon began no differently. Fresh observational data had just arrived from the Global Telescope Network. She loaded the measurements into the model and waited as the calculations updated the object's path through space. When the results appeared, she expected the usual pattern, a slight correction that would bring the trajectory back toward earlier predictions. Instead, the opposite happened. The projected path shifted again in the same direction it had moved weeks earlier. The change was subtle but unmistakable. The predicted route was drifting toward a boundary she had been watching carefully ever since the object first appeared in the dataset. She paused and pulled up the previous version of the model. On the screen, she placed the earlier prediction over the new one, comparing them point by point. Two sets of observations, collected during two different viewing periods, had produced two separate revisions, yet both changes were pushing the trajectory in exactly the same direction. The path was slowly sliding inward, closer to the outer limit of Jupiter's gravitational sphere of influence. She leaned back in her chair, not dramatically, just the quiet movement of someone who has seen numbers that don't quite match expectations. When orbital calculations behave like this, it means something important may have been overlooked. Without wasting time, she called the senior analyst. He opened the same overlay on his screen and studied the data in silence. For 11 seconds, neither of them spoke. Then he asked her to repeat one critical step. Run the outgassing correction again. Interstellar objects often release jets of gas when sunlight warms their surfaces, and that tiny thrust can nudge their trajectories slightly. If the model had not accounted for those forces correctly, the drift could simply be a mathematical artifact. She ran the correction again, with the full non-gravitational adjustments applied. The computer recalculated the path using every known physical influence acting on the object. The result did not change. Even after accounting for outgassing and all other measurable forces, the revised trajectory placed the interstellar visitor known as 3I Atlas closer to the boundary of Jupiter's gravitational region than any earlier estimate had predicted. Two independent revisions, both pointing the same way, and no modeling error to explain them. She picked up her phone, but not to call another department. Instead, she opened the calendar. She already knew the answer, but wanted to see the number clearly. 18 days. After March 16th, the observation record would stop, not pause, not slow down, but stop completely. By then, the object would accelerate beyond the practical tracking range of every telescope on Earth and every instrument currently in orbit. Once it left that observational threshold, it would never return. Whatever the orbital model showed on March 16th would become the final answer humanity would ever get from this visitor. And right now, that answer was shifting toward Jupiter in a way the early predictions had never anticipated. This is not simply a story about a cosmic flyby. It is the investigation of a closing window in which the physics of the solar system is about to interact with an object that came from another star. Two small trajectory revisions might appear minor on paper, but in orbital mechanics, They can reveal patterns that change the entire interpretation of an encounter. To understand why those revisions matter, you first have to understand how astronomers predict the motion of objects moving across the solar system. Every observation recorded by telescopes becomes a data point. Scientists build what is called an ephemeris, a detailed time-ordered table that predicts where the object will appear in the sky at every moment. Those predictions combine measurements of position, velocity, and direction with the gravitational influence of the Sun, the planets, and the major moons. As more observations arrive, the model becomes sharper. One revision is normal. That is how science improves its accuracy. But two revisions in the same direction, two independent corrections pushing the predicted path toward the same gravitational boundary, begin to form a pattern. And patterns in astrometric data are how the universe quietly reveals that an earlier model was incomplete. Over 200 observatories across several continents had been tracking 3I Atlas, creating the largest coordinated observation campaign ever conducted for an interstellar object. When that enormous dataset was combined, the refined model placed the object slightly closer to the outer edge of Jupiter's gravitational region than originally expected. Scientists noted the shift and continued monitoring. Then, a new source of data arrived, information captured near Mars by spacecraft instruments capable of far greater positional precision than any ground-based telescope. When those measurements were added to the calculations, the trajectory changed again. And once again, it moved in the same direction. Two different observation systems, two independent refinements, one converging result. The predicted path of 3I Atlas was drifting toward a region of space that has a very specific name in celestial mechanics, the Hill sphere. And as the next section begins, that boundary will turn out to be far more important than it first appears. The path of 3I Atlas was no longer just a line on a screen. With each new observation, that line was slowly moving toward a region of space that astronomers treat with particular attention. This region is known as the Hill sphere, and understanding it is the key to understanding why those two quiet trajectory revisions at the Jet Propulsion Laboratory suddenly mattered so much. In simple terms, every massive object in the solar system controls a zone where its gravity becomes the dominant force acting on nearby objects. That region is called its Hill sphere. Outside that boundary, the Sun's gravity remains the primary influence. But once something crosses into the Hill sphere of a planet, the balance changes. The planet begins to take control of the interaction. The concept was formalized in the 19th century by mathematician George William Hill, who developed the mathematical framework describing how gravitational dominance shifts between bodies moving through space. For most planets, that region is modest. But Jupiter is not a typical planet. With a mass more than 300 times that of Earth, it possesses the largest gravitational domain in the solar system after the Sun itself. Jupiter's Hill sphere stretches roughly 53 million kilometers from the planet's center. Any object passing within that distance enters an environment where Jupiter's gravitational influence begins to compete directly with the Sunday. The revised orbital model now suggested that 3I Atlas would approach this boundary far more closely than scientists originally predicted. The difference may sound small, but in orbital dynamics, small differences can translate into dramatically different physical outcomes. A distant flyby where Jupiter's gravity barely nudges an object is one scenario. A closer approach, where the planet's tidal forces actively act on the object's structure, is something entirely different. In the first case, Jupiter is little more than scenery in the background. In the second case, Jupiter becomes an active participant in the encounter. And when Jupiter participates, the interaction is powerful. To see why, Consider the concept of tidal forces. Gravity pulls an entire object toward a massive body, but tidal forces work differently. They arise because gravity is stronger on the side of the object closest to the massive body and weaker on the far side. That difference creates a stretching effect across the object's entire structure. It is the same phenomenon that causes ocean tides on Earth under the influence of the Moon. On a planetary scale, however, the effect can become far more intense. For an interstellar object like 3I Atlas, the size of that tidal gradient depends on two main factors: the mass of the planet it passes and the distance of the encounter. Jupiter's immense mass means that even a relatively distant pass can create measurable stress across a body moving through its gravitational field. The object itself is not small. Observations suggest a nucleus measuring roughly 2.6 kilometers in diameter. That makes it significantly larger than the earlier interstellar visitor known as 2I Borisov. When a body of that size moves through the steep gravitational gradient near a giant planet, the forces acting across it become mechanical rather than theoretical. Real stresses are applied to real material. What happens next depends entirely on the object's internal composition. If the nucleus is loosely bound, the differential forces could fracture its structure. If it contains volatile materials, the heating and stress could trigger bursts of outgassing that alter its velocity. In more extreme cases, tidal forces can even break objects apart, creating fragments that continue on slightly different trajectories. The problem is that scientists still do not know the exact internal structure of 3I Atlas. Ground-based observations have revealed important clues about its motion and brightness, but they cannot directly resolve its composition. That uncertainty is precisely why the Hill-sphere boundary becomes scientifically decisive. An object passing well outside that region experiences only a small deflection, but an object passing near the edge of Jupiter's gravitational dominance enters a much more complex environment where tidal forces, velocity changes, and structural stress all begin to matter. The twice-revised trajectory now placed 3I Atlas close enough to that boundary that these possibilities could not be ignored. It was not on a collision course with Jupiter, and the orbital solution still described a hyperbolic flyby. In other words, the object would not be captured by the planet's gravity. Instead, it would swing past and continue outward, accelerating back toward interstellar space. But during the hours surrounding that close approach, Jupiter's gravitational field would leave its mark. Tidal forces could stretch the object. Gravitational slingshot effects could alter its velocity. Even small structural changes could reveal clues about the composition of matter formed around another star system. And here is the most important detail. This encounter would happen only once. After passing Jupiter, 3I Atlas would gain enough speed to move beyond the tracking limits of current observational technology. No telescope planned or operating today would be able to follow it indefinitely. Once it crossed that threshold, the data stream would fade and eventually disappear. Every measurement, every image, every spectral signature, every positional update had to be captured before that moment arrived. Because when the observation window closed, the file would close with it. The object would continue its journey through the galaxy, carrying information about its origin, its chemistry, and its structure. But unless that information was captured during the short period of visibility inside our solar system, humanity would never see it again. Which is why the next question became unavoidable. If this encounter near Jupiter could reveal so much about an interstellar object, was there an instrument already close enough to observe it properly? The answer was yes. And that answer leads directly to the most controversial decision in the entire story, the decision involving a spacecraft already orbiting Jupiter, equipped with exactly the instruments needed to study the event, yet ultimately not redirected to observe it. In the next part, we examine that spacecraft, the proposal that was submitted to use it, and the unexpected decision that left one of the most valuable observation opportunities in modern astronomy slipping quietly out of reach. The closer scientists looked at the predicted encounter between 3I Atlas and Jupiter's gravitational boundary, the more obvious one fact became. The best instrument capable of observing this moment in detail was already there. Since 2016, a spacecraft has been orbiting Jupiter, repeatedly diving close to the giant planet and collecting data about its atmosphere, magnetic field, and interior structure. That spacecraft is called Juno. Its mission was designed to study Jupiter itself, but the instruments on board happened to be almost perfectly suited for something else, as well observing complex interactions between objects and the Jovian environment. Juno carries a visible light imager capable of capturing high-resolution pictures. It also includes an infrared mapping instrument that can detect heat signatures and analyze the composition of gases and surfaces. In addition, the spacecraft is equipped with sensors that measure radio emissions and plasma waves, tools designed to observe how particles and electromagnetic forces behave around Jupiter. When scientists compared those capabilities with what might happen during the 3I Atlas flyby, the potential became obvious. If the interstellar object passed close enough to Jupiter's Hill sphere boundary, the planet's tidal forces could cause measurable effects. Jets of gas could erupt from the surface. The nucleus might fracture. Charged particles could interact with Jupiter's enormous magnetosphere. Each of those events would produce signals that Juno's instruments were specifically built to detect. Even more important was the spacecraft's position. During the predicted encounter window, Juno's orbital path would place it on the sunlit side of Jupiter within observational range of the approach corridor. In practical terms, that meant the spacecraft could potentially capture images and data that no telescope on Earth could match. From the perspective of planetary science, this was an extraordinary opportunity because the truth is that ground-based telescopes, no matter how advanced, face limits that spacecraft simply do not. Observatories on Earth must look through the planet's atmosphere, which introduces distortion and reduces precision. Their viewing angles are restricted by geography and weather. Even the most powerful observatories cannot match the positional accuracy of a sensor operating directly in space near the target itself. Juno, by contrast, was already inside Jupiter's environment. It was operational. Its mission had been extended through 2029, and the spacecraft still had the ability to perform small trajectory adjustments if required. Recognizing that potential, a formal proposal was submitted. The idea was straightforward: slightly redirect Juno's observation schedule during the encounter window so its instruments could capture targeted data on 3I Atlas as it approached Jupiter's gravitational boundary. The proposal moved quickly through the review process. Scientists outlined the possible measurements in detail. They described how Juno could examine the object's nucleus morphology, detect possible fragmentation, measure electromagnetic emissions, and analyze any jets of material released during the gravitational interaction. The request also addressed technical feasibility. The maneuver required to adjust Juno's orientation and observation plan was small. The necessary change in velocity, known as delta V, was well within the spacecraft's operational limits. In short, the science case was strong, the technical requirements were reasonable, and the timing was critical. Because the opportunity could never happen again, unlike many astronomical events that repeat or remain observable for years, the passage of 3I Atlas through the inner solar system was temporary. Once it accelerated beyond Jupiter and continued outward, the object would vanish from the reach of current instruments. This meant the proposal carried an unusual sense of urgency. The encounter window was narrow. Decisions needed to be made quickly if Juno was going to participate. For a moment, it appeared that might happen. The proposal was peer-reviewed and scored well enough to be considered for approval. Scientists involved in the effort believed the case had been clearly made. Then the decision arrived. The proposal was rejected. The entire process took less than 48 hours. The official explanation cited two main reasons. First, mission planners pointed to fuel reserves. Juno's remaining propellant, they argued, had already been allocated to support the spacecraft's primary mission objectives. Second, they emphasized that the spacecraft's focus remained on studying Jupiter itself, not passing objects moving through its gravitational neighborhood. On paper, those explanations seemed reasonable. Space missions operate under strict resource constraints, and priorities must be carefully managed. But when scientists compared the rejection with publicly available mission extension documents, some began to question whether the reasoning fully held up under scrutiny. The requested maneuver had been within operational parameters. The spacecraft would have remained capable of completing its scheduled observations, and the scientific value of observing an interstellar object interacting with Jupiter's gravitational environment was difficult to ignore. In practical terms, the decision meant something very simple. The most capable observational instrument within range of the encounter would not be used. As a result, the record of 3I Atlas would close with gaps that Juno might have filled if it had been pointed toward the object during those critical hours. And once those hours passed, those gaps would become permanent. The significance of that decision extends beyond a single spacecraft or a single interstellar visitor. It reveals something deeper about how modern science responds to opportunities that appear suddenly and vanish just as quickly, because the universe does not schedule its events according to human timelines. Sometimes it presents a narrow observational window, and if the systems designed to respond cannot move fast enough, the moment simply passes. The encounter with 3I Atlas is beginning to show exactly where that gap exists. And in the next part, the discussion moves beyond orbital mechanics and spacecraft decisions to a much larger question: what this moment reveals about humanity's readiness to respond when the universe sends us a rare and non-repeatable opportunity. When the decision not to redirect Juno became final, something unusual happened inside the scientific community. The conversation quietly shifted away from the object itself and toward a broader question. The trajectory of 3I Atlas had already shown how well modern science can track and predict the motion of objects moving through the solar system, but the missed opportunity to observe the encounter up close exposed something else entirely: a structural gap between what scientists can calculate and how quickly institutions can respond. The physics of the encounter was never the problem. Researchers knew exactly what could happen when an interstellar body approached the edge of Jupiter's Hill sphere. The gravitational gradient could stretch the object. Jets of gas might erupt as stress traveled through its internal structure. Small fragments could break away if the material was weak enough. Even subtle changes in velocity could reveal how mass and energy were distributed within the nucleus. Every one of those outcomes would generate signals that modern instruments are capable of measuring. What scientists lacked was not knowledge, but speed. The proposal to use Juno demonstrated that the technical ability to observe the event already existed. The spacecraft was operational, its instruments were functioning, and its position in orbit placed it within range of the encounter corridor. The calculations had been done, the science case had been published, and the opportunity had been clearly documented. Yet the system responsible for approving that observation could not move quickly enough. The review process that handles guest investigator proposals was originally designed for a different pace of discovery. Most space missions plan their observation schedules months in advance. Researchers submit proposals, Committees evaluate them, and the final selections are implemented gradually. That approach works well for predictable targets such as planets, moons, or distant galaxies. But interstellar objects are not predictable. They appear without warning, cross the solar system once, and disappear again. Their trajectories move quickly enough that the most valuable observation window may last only a few days. In the case of 3I Atlas, the useful redirection window for Juno was measured in days, not weeks. The standard review cycle simply could not keep up. That mismatch between physical opportunity and institutional response is what turned this encounter into something larger than a single astronomical event. It became a case study in how modern scientific infrastructure handles sudden discoveries. And discoveries like this are expected to become more common. In the coming years, a new observatory will begin scanning the sky with unprecedented speed and coverage. Known as the Vera Rubin Observatory, it will repeatedly photograph large sections of the night sky, creating a continuous record of moving objects across the solar system and beyond. Its powerful survey system is expected to detect many more interstellar visitors, possibly several each decade. Each detection will present the same challenge. An object will appear suddenly in telescope data. Scientists will calculate its trajectory and determine how long it will remain observable. Somewhere within the solar system, spacecraft may already exist that could study it more closely. But whether those spacecraft are redirected in time will depend on how quickly the decision process can operate. The experience with 3I Atlas has now made that challenge visible. The gap between detection and optimal response is not a lack of knowledge. Scientists understood exactly what Juno could have observed during the encounter. They published the calculations and described the measurements in detail. The problem was architectural. The system responsible for approving those observations was built for slower events. Physics did not wait. By the time the decision process finished, the useful observation window had effectively closed. What remains is a permanent record showing exactly what was possible and exactly what was not authorized. In that sense, 3I Atlas has already become part of the planning framework for the future. Every discussion about flexible spacecraft operations, reserve fuel allocation, and rapid response observation programs will point back to this event as a real example rather than a hypothetical scenario. There is another way some scientists have tried to frame the significance of this moment. They borrow a perspective from theoretical physics often associated with the work of Michio Kaku and other researchers studying the long-term development of civilizations. In that framework, sometimes called the Kardashev scale, civilizations are classified by the amount of energy they can control and the technological systems they build to interact with the universe. A civilization approaching Type 1 status can manage planetary resources. A Type 2 civilization can harness the energy of its entire star, but energy alone is not the full story. Response capacity matters as well. How quickly can a civilization react when the universe presents a rare and unrepeatable opportunity? How flexible is its infrastructure when something unexpected appears within reach? Through that lens, the encounter with 3I Atlas becomes more than a scientific curiosity. It becomes a practical test of readiness. Humanity succeeded in several important ways. We detected the object. We tracked it using more than 200 observatories. We refined its trajectory twice using increasingly precise data. That is genuine progress compared with the situation only a few decades ago. But we could not redirect a spacecraft in time to capture the most detailed measurements. That gap between capability and response is now written permanently into the record of this event.